Hello everyone, this is Matteo from Starway Design. Welcome to the video number 2 in the Microchip Polarfire SoC series. Today we're creating a basic design for the Polarfire SoC video kit from scratch. While in the previous video we've seen how to build the reference design, it's important to be able to create a design from scratch. Until you do, you might miss some important details. We're going to create a custom MSS configuration and an FPGA design with 2 GPIO banks connected to LEDs and dip switches on the video kit. We're going to add support for the GPIO banks to the Linux kernel and write some example in Python for testing. In this video, as you will watch the first video of the Microchip Polarfire SoC series, where I explain how to install the tools, build the HSF firmware, Yocto image, etc. Full disclaimer, this video is not sponsored by Microchip and the video kit has been bought by Starway Design. Command lines, links, etc. are available in the blog post on the Starway Design website. Let's begin. Let's create a new directory for this project and a new directory for the MSS configuration. Then copy the MSS configuration from the reference design. The MSS configuration has the DDR4 memory configuration, and since we're using the same board, we can use the reference design as a starting point. Open the config file. To understand which peripherals we should keep, open the reference design so it is easier to see how each peripheral is used. We keep eMMC and SD, USB, Ethernet MAC 0 on 1, UART 0 and UART 1 used for the HSS and the Linux console. We can disable I2C 0 since it is used to configure the cameras. GPIOs from bank 2 are used for the SD card and for the USB file reset, so we keep them. GPIO2, Fabric are used for LEDs and signals related to the camera interface and video pipeline. We can remove them since we're going to add a bank of GPIOs inside the FPGA fabric. Regarding the MSS2 from Fabric Interface Controllers, we don't need FIC1. That is used by the video pipeline to write into the MSS memory. We don't need the embedded DLL. It is required if the APV clock frequency is equal or greater than 125 MHz. From a clocking point of view, we keep all the clocks based on the dedicated ref clock on bank 5 as in the video reference design. Click on Edit and Edit Settings and change the module name to Basic Design MSS. Note that this name needs to be different from the top-level design entity in the FPGA. Save the changes and generate the output files. As described in the previous video, there are 2 files we need: the XML for the FPGA project and the CFG file for the hard software services. Create the directory name FPGA and start libero. Click on New Project and create a new project called Basic Design in the FPGA directory. The target device is the MPFS250TS-1FCG1152I. In device settings, keep the default configuration and click on Finish. Create a new smart design that will be the top-level entity for this design with file New Smart Design. Name it Basic Design. Now let's import the MSS configuration with file import MSS component and select the file we have generated with the MSS configuration. Do a right-click on the Basic Design MSS and instantiate it in Basic Design. let's add 2 blocks of GPIOs to connect to the LEDs. Of course, we could use a single GPIO block, but I want to show how to handle multiple IP on the IPV bus. Since we're going to use the GPIOs with the Linux device driver provided in the kernel, you have to configure the GPIO banks not to use a fixed function, input or output. While this would use fewer logic elements, you will not be able to use the GPIOs as input. When configuring the GPIOs as a fixed function, the configuration register is not present and will always read zeros. The GPIO get function checks the configuration register, and if the GPIO is configured as output, it will read the output register. Otherwise, it will read the input register. But if the GPIO bank is configured as a fixed function, the configuration register always reads 0, which means output. So the GPIO get function will never read the input register. Let's create a port for the LEDs and one for the dip switches and connect them to the GPIO blocks. Instantiate a core APB3 block as the interconnect between the 2 blocks of GPIOs and the MSS. We can see 2 GPIO blocks mapped into the MSS memory space. Regarding the clock and reset, we just need a clock in the 50 to 100 MHz range. There is a 50 MHz single-ended oscillator on the board. Add a reset block and a Polarfire init monitor. Connect the init done between the reset block and the init monitor. Connect the fabric power on reset from the init monitor to reset block and the MSS reset input. Connect the MSS reset output to the external reset input of the reset block. Connect the fabric reset output from the reset block to the 2 GPIO blocks. Connect the MSS and the 2 GPIO blocks to the 50 MHz clock. Also tie high bank VDDI status and PLL lock, and tie low SS busy and FFUS restore. Connect the APB clock input to the 50 MHz clock. Click on Promote to the top level for the UART signals to create ports with the same name as the signals on the MSS. There are a few more signals to tie high-low for the Ethernet PHY. VSC 8662 CMOD 3 to CMOD 7, or low except CMOD 6. VSC 8662 as reset die high. The CMOD signals are used to set the default PHY configuration. Also connect the VSC 8662 reset N to the MSS reset. Ties low the GPIO inputs and the interrupts. Click on the design rules check and you shouldn't get any errors. Click on Generate Component. Let's copy the constraints for the Ethernet PHY and the two UARTs from the video kit reference design. And then create another constraints file for the LEDs, dip switches and clocks. And we copy the following. Then we create a timing constraints file for the 50 MHz clock. Select the basic design as root instance. Use the Constraints Manager to enable the 4 PDC files for the I/O attributes and 1 SDC file for timings. And now build the bitstream. You might have noticed that we didn't create pin assignment constraints for all the I/O ports on the block design. We create the pin assignment constraints for the UARTs, but not for the Ethernet. Let's open the MSS configuration again. If you look at the I/Os, some are fixed, like for the Ethernet, and some are fabric, which means that for the fixed signals, even if they appear on the block design port, they don't need the pin assignment constraint. On the block design, you can see the fixed signals have a different color and the ports were created automatically when imported the MSS configuration in Libero. Let's flash the bitstream on the FPGA. If you're switching between projects, don't use Open Recent Project directly, but close the current project, otherwise Libero doesn't find the license for the device. Now that we have a bitstream on the FPGA, let's create the hard software services firmware. Check out the HSS source code and start with the video kit default configuration. Now point the config file to our custom file. Build the HSS and flash it to the board. Clone the repository with the repo manifest. Sync the repo. And now initialize the environment. Note the dot at the beginning of the command line. Let's build the development image for the video kit as is. Add the Python GPIOD package to the image. We're going to use it to write a few test scripts later in the video. The last line is to avoid errors when building the image with DevTool. Export the board we're going to use, or you could edit the local config. Now we want to modify the DTS for the video kit to add support for the two banks of GPIOs. Add to the Polarfire video kit device tree a clock source and the 2 GPIO banks. The memory addresses are from Libero SoC. Let's build the kernel. Build the image to test it. Unmount the SD card. In this case, I have written the SD card previously, so I unmount the boot and root partitions. And now write the image. Let's find the IP address of the board and SSH into it. Let's find the GPIOs controllers to use. The first GPIO controller is the one in the MSS, and the other two are the ones in the FPGA fabric. Let's write the first example to print the information of the 2 GPIO banks we have added. Now we can write the second example, blinking one of the LEDs every second. And you can see the LED blinking. Now for the last example, let's read the status of the inputs every second. Now commit the changes we've done to the Linux kernel so we can create a patch. We're going to create a new meta layer that we're going to use for our kernel patch. And add it to the bitbake build environment. To export your commits as patches and create a bb append file, use the following command. And build the image, flash it to the SD card and test it again. That's all for this video. We've seen how to create a custom MSS configuration and basic FPGA design, build the HSS, modify the Linux kernel, and test everything on the board with some Python scripts. If you liked the video, let me know in the comments which topic you'd love to see next. Hit the like button, subscribe for more.